is the other side of the nervous system. We talk about the somatic system, that is more of a voluntary control over muscles. The autonomic system is the other side, which is more of an involuntary control over smooth muscle, cardiac muscle, glands. Okay? The brain ultimately is the controller over autonomic function. What is talked about in this chapter is the architecture of the system, if you know what I mean. Architecture meaning how do the impulses get to the internal organs, the smooth muscle, the glands, the cardiac muscle. So there's a lot of that that's talked about in this chapter. Ultimately, the chapter ends by saying, hey, look, it's the hypothalamus that controls all of this. Okay? So what do we learn? We learn that there appears to be two separate nervous systems that control the internal environment. Okay? And oftentimes, and it's talked about throughout this chapter and in my lecture, it's oftentimes thought of that the two divisions of the autonomic system work against one another. That where one may excite an effector, the other one inhibits an effector. And that is typically true. However, you will find plenty of examples of where the two systems antagonize each other and lead to homeostasis. Okay? What do I mean by antagonize? One turns something on, the other turns something off, but they turn them on and turn them off at the right times, and homeostasis is the result. Okay? Receptors on the membranes of ANS effectors vary. APs reaching an effector may not stimulate it to action. ANS, autonomic nervous system, effectors means any target for this system. Typically glandular tissue, okay? Glandular tissue. Typically smooth muscle tissue found in a bunch of different organs. And then cardiac muscle, which we know is in one place. So the receptors on these effectors vary. And when the nervous impulse reaches the effector could be stimulated by this impulse or inhibited by the impulse. Okay? All right. Speed of transmission in the ANS is a bit slower than the SMS. What's the SMS? Motor. Somatic motor system, or SNS. Somatic motor system, or SNS would be somatic nervous system. But either way, the somatic system typically uses myelinated fibers. The autonomic system typically does not use myelinated fibers, although there's quite a bit of variability there. Who cares? Well, if you are pretty good with understanding why the somatic motor system needs to operate so quickly, then you might understand why perhaps the autonomic system doesn't need to activate as quickly. Okay? A slower process to turn on glands and organs and to turn them off. Not a big earth-shattering thing, just a different architecture once again. Finally, another link between nervous and endocrine systems is demonstrated here. We've already heard about how the hypothalamus controls the pituitary. That is an important link. I've given you an example about how something you see can influence hormone release in your body. Something you hear. That is also present in this system as well. And that is turning on one side of the sympathetic system leads to hormone release directly. Okay, so nervous tissue actually turning on endocrine organs. You may remember that the ANS is broken down into two divisions. The sympathetic, I always had to try to remember how to, let's say, link sympathetic to what it did. And what I did was I thought about how sympathy, when someone, let's say, when you get into a difficult situation, you need some sympathy. And it is in difficult situations that the sympathetic system activates, typically. That difficult situation could be fear or threats, need to run away, need to do battle. It could mean that you're exercising, which is a little bit outside of the ordinary, okay? All right? I don't have such a device to help me remember parasympathetic. It's just obviously not sympathetic, okay? Parasympathetic, then, is what's happening when you're in a room like this, unless you're really stressed out right now. if you're not stressed out, if you're reasonably calm, your parasympathetic system, the rest and digest system, is the dominant system here. What gets confusing is that all the signals are coming pretty much from one place, more or less. It's just which architecture is being used. Is it sympathetic nerves that are being used or parasympathetic nerves that are being used? Okay. Dual innervation. There are exceptions to this, and I'll tell you about those in a moment. Dual innervation is simple. It means that sympathetic fibers go to a gland or an area of smooth muscle, and parasympathetic fibers go there. They both go to the same organ. However, they're going to lead to different effects, oftentimes opposite effects, but not always. Okay? So that's what dual innervation says. Now here's an important exception that you need to know about. Okay? The sympathetic side, the fight or flight that you may have learned about a long time ago, called it that. Maybe you have learned it from me as the 3 E's or the 4 E's, exercise, excitement, emotion, embarrassment, all of those things. The sympathetic division innervates exclusively blood vessels. Okay, and sweat glands. Now this may not actually lead to you changing anything you do today, but blood vessels are controlled, their diameters, they have smooth muscle in their walls. And the diameter of a blood vessel is controlled by stimulating the smooth muscle to relax or contract. Okay, stimulate it to contract, take away stimulation, get it to relax. That's only done by sympathetic fibers. Now let's think about when the sympathetic activates. Okay, it activates under the 3E conditions. And so the blood vessels are going to be fine-tuned by the sympathetic system all the time in order to maintain blood pressure and maintain blood flow to certain areas. Okay, but under those 3E conditions, when we're not, not just baseline conditions, when we get into that excitement, emotion, exercise conditions, then control over the blood vessels is even more important. Okay, we need to control blood pressure right now. Okay, but then we also need to alter blood flow when we start to exercise, send blood to some places, not to others, and so on. So there is some logic in the sympathetic controlling only the blood vessels. This parasympathetic does not. And the sweat glands, again, if you think about exercise, now we have a constant supply or constant sweating, okay? You don't notice it typically, so you can't say that the sympathetic system only functions during these 3E conditions or 4E conditions, if you're following me on those E things, okay? Sympathetic system is active now in you, but if you begin to exercise, you know that it will stimulate more sweating than what is occurring right now. Are you sweating now? Yeah, a little. Of course, you know it really ramps up when there's a great need. Okay? So those are exceptions to the dual innervation. You'll probably go into tomorrow just same as you were today after learning these things, but they do make sense. The sympathetic needs to control blood flow under emergency or 3E or 4E type conditions. It needs to control sweating as well. Dynamic antagonism is just a fancy way of saying that the two systems actually do work together, even though they may antagonize. Even though one system may turn on something and the other system turns it off, it still leads to homeostasis. Most spinal and many cranial nerves contain both somatic and autonomic fibers. So we're seeing the first example of, or first statement of the architecture of the system. Okay? Most spinal and many cranial nerves contain both somatic and autonomic fibers. You know what this means. These are voluntary motor fibers, telling skeletal muscles to contract. What this is simply saying is that the autonomic system may use existing nerves to get to the effectors that it needs to get to. However, maybe today, maybe not, you'll learn that the autonomic system actually does have certain dedicated nerves that it uses as well. Okay? So if we go in here and pick any spinal nerve, okay, we're likely to find autonomic fibers in there, and as well as somatic fibers. But we will see that the autonomic system will use its own nerves too. Okay? All right? The features, this more or less comes from your book, more or less. These are motor neurons. They are telling body parts to do something. They're not collecting sensory information. They are sending instructions. So they're motor neurons. They innervate smooth muscle, which is everywhere. The reproductive system has a bunch of smooth muscle in it. Okay? Orgasm is something that is controlled by the autonomic system. You may wish to have an orgasm, but it doesn't happen until there's a series of events that occurs. Okay? All right? Smooth muscle in the blood vessels. Smooth muscle in a number of organs. The complete digestive tract is all lined with smooth muscle. Okay? Glands are things like sweat glands. They are glands which might produce a mucus. Okay? They are glands which may produce a hormone. Okay? And others. Ensuring optimal support for daily activities. It is unconscious for the most part. We have talked a little bit about how maybe biofeedback might allow you to maybe have an influence on certain autonomic function, but not wholesale control. It goes on behind the scenes. Visceral is a term that is sometimes used. Visceral means the guts. This tends to be a system that controls the guts. But obviously skin's glands are not what we consider gut, but they are body related. Target tissues are either stimulated or inhibited. We can inhibit a tissue by actually releasing an inhibitory neurotransmitter, okay? Or we can excite a muscle or gland by releasing an excitatory neurotransmitter. It depends on which neurotransmitter is released and what the target tissue possesses as its receptors. If a target tissue does not possess a receptor for a particular neurotransmitter, no response. Two synapses from brain to effector. A preganglionic neuron, an autonomic ganglia, and a postganglionic neuron, and then the effector. I wish we would have had a little bit more time to work with peripheral system and we talked about 3 neurons in the sensory system, the afferent system. We talked about 2 neurons in the voluntary motor system, okay? Upper motor neuron, lower motor neuron, you had a question about it today, okay? All right? This system uses kind of what they call a preganglionic neuron and a postganglionic neuron. Your preganglionic neurons are central nervous system neurons, and your postganglionic neurons are found out in the body somewhere. Here's the big difference. There is a place where the two meet. In the CNS, a upper motor neuron and a lower motor neuron meet within the spinal cord, okay? In the ANS, if you want to call it the upper motor neuron, the preganglionic neuron is in the CNS, and then it goes out to a lump of tissue. That lump of tissue could be along here, okay, or down in here, and it meets with its postganglionic neuron there. And then message is passed along to the effector. A little bit different. Again, maybe not earth-shattering. Tell me something that's earth-shattering, because we'd like to talk about it. It's been a tough day today. It's your nervous system you're stuck with, okay? The primary neurotransmitters used. You might search for relevance. One of the nice things about the autonomic chapter is it actually brings together what you've learned prior to this point. okay? We've talked about architecture, we've talked about neurotransmitters.